That's fine. Hopefully I don't make this too loud, but the audio should be on. All right, everyone. Welcome to Understanding Bitcoin Source 7. This is not BitDevs. This is like my own unique event. And yeah, you could attribute anything I say to me. Obviously, I'm filming myself. It's on Twitch. This is happening right before BitDevs. It's going to be 7:30, and that's Chatham House rules and all that. But here are different rules, so feel free to ask me any questions. But today we're going over Bitcoin addresses. So what they are and how they're generated, because they're generated differently depending on what type of output you have, and I'll kind of go over all of that stuff. And I'll try and make it interactive and ask questions. I think Prem can help with that, with the question asking. Or did you want a pseudonym, like Blue Banana? Okay. So what is a Bitcoin address? Can any of you guys help me out with the answer?
It's a representation of where Bitcoins can be sent to.
Yeah, it's like a destination. A lot of people see Bitcoin addresses as something cryptic, like it's a string or like a piece of text.
Mailing address.
Huh?
A mailing address.
Right, like a mailing address. But people think mailing addresses sound better because they're easier to remember with words. Bitcoin addresses, there's not really any coherence to it. Or so you'd think, it seems like a random sequence of text. But we use random sequences of text in a lot of different ways, right? If you think of your phone number, right? Area codes have some coherence to them. And addresses have something like area codes in a way, which we'll go into. ACH, routing numbers, and all that. So, yeah, it seems like random sequences of text, but they're not, and we'll see Bitcoin addresses aren't either. So, I have an answer for what is a Bitcoin address. A Bitcoin address is a piece of text that's generated by a wallet that allows other wallets to send money to it, right? It's like, if I want to receive money from any of you, I can give you my address, and you guys can send me Bitcoin. And all that's great. If you guys have ever seen an example of a Bitcoin address, here's two Bitcoin addresses. This is an OpenSats address, and this one is a first spendable address that I see from the second block. That's getting the Coinbase, and pretty cool. If you ever go on the Block Explorer, you could see these. They mean different things, and that's why they kind of look different. So how does an address relate to transactions on the blockchain? I've gone over a concept called the script pub key in the past, but I can go over it again because I want to make sure that you guys get it really good in your head. In fact, can anyone tell me what a script pub key is today? Anyone? No?
It's the script which to execute and unlock the particular output.
Yeah, so script pub key is like the locking script is sometimes what I like to call it, of your Bitcoin. It kind of changed a little bit after SegWit. Instead of having a script that locks the Bitcoin sent to you or your UTXO, with SegWit, it's actually something called the witness program. So it's like this hash. But before that, when we had legacy addresses, it was the actual locking script or the program. And most of these locking scripts look like pretty much asked, hey, give me a public key that matches, that I can hash to create this hash that's in the locking script, and also give me a signature for this public key that covers the transaction you're trying to make. So yeah, pretty much these old scripts used to ask for your entire public key, since the locking script would only reference a hash to it, and you'd have to give it your signature. But what do I have here? I said Bitcoin consensus forces every transaction to have at least one input and one output. There's some weirdness in the amounts. I don't know if you guys follow inscriptions, but Super Testnet, he did a very funny thing with a Bitcoin transaction where he did make it 0 input, 0 output, and messed up a lot of people's calculations. Because, very interesting. So, Bitcoin consensus, it forces every transaction to have at least one input and one output. Every output has an amount. So, if Blue Banana sends me one Bitcoin, his transaction will have one output to me let's say he only has one Bitcoin to his name, he sends it all to me. It's also going to have, it pretty much just has the output and this locking script. So this is a snippet of the code, and these are, two parts of a transaction. It's kind of small on here, and I know it's truncated on the screen, but the end value is the amount, and script pub key is this locking script. It's part of the transaction data that determines who can spend the output, and the address is actually created from the script pub key. And I just realized my camera kind of blocks some of it, but it's okay. Because I'm reading it out. So a good question is like, how can I find all the transactions that are spending to a particular address? Based off what I said, do you have any suggestions? How'd you go about, or I can read it too. But, well, there's an algorithm that we can use that can turn the script pub key into an address. So again, the script pub key is this locking script, and you could actually perform an operation on this locking script to create an address. There are algorithms that convert the address text to a script pub key, and that is what the main thing I'll be going over today. And after we run the algorithm and we get the script pub key, then we can compare every output's script pub key. So every transaction I see on the blockchain, I could look at it, look at every single output, and look at the locking script of every output. And then I can, compare that script pub key to the script pub key that I used to create my address. Let's say I'm looking for all the outputs that were directed to me in the history of the blockchain.
So I do have a question.
Yeah.
So the turning of the script pub key into an address, it follows an algorithm. This algorithm it's not a hash, right? It's not a one-way thing, right? Like
it is.
Oh.
Yeah, it is one way. It involves hashing. It's not just the hash. But yeah, it involves hashing. Yeah. So you can't actually get the public key from, at least with respect to legacy addresses, and I'll go into SegWit addresses as well. But yeah, you cannot get the public key from the address, and you will see why. So after we run the algorithm and we get the script pub key, we can get the output script pub key, blah, blah. Most block explorers do this once for all transactions, and they store data in a way to make it easy to get all the transactions related to an address using a process we call indexing. So Explorer, if you ever use that, a block explorer, mempool.space, when you go and you look at the page for an address and you see a balance there, it's because there's been some processing in the background that's looked through every single transaction, looked at every output of those transactions, and looked at a script pub key to see which address it could match, right? Because you can always generate an address from a script pub key. Cool. Yeah.
So for script pub key, the reason that they don't just put the value and then your public key is because script pub key could not just be a simple send everything to one person, but have multi-sig stuff and all that. That's why you store the actual script.
Yeah.
That's why you send the script. Okay.
Yeah. So you can have more complex scripts. I actually don't even need to ask for a signature at all. I could say there is something with script pub keys where it doesn't allow you to have two small script pub keys, but you could do things where you could pad it. But I was gonna say you can make a script that pretty much asks anyone to provide the answer to 1 + 1, right? And then if you were able to give, I don't know if you guys remember, but script sig for legacy transactions, you could give it pretty much like an unlock script to the locking script that is like, oh, this is 2. That equals 1 + 1, and you could spend a transaction that has a simple script like that. The problem with simple scripts like that aren't bound to a public key and don't ask for a signature is that if you can answer it and put it in the mempool, and I'm a miner, and I see that you're trying to spend to your address.
The miner can also.
Right, exactly. I'll be like, oh, that's the answer to it. I'm just gonna take this UTXO and put my own unlocking script. I know what 1 + 1 is. It's 2 because he had the answer there. And I'm gonna make a new transaction with the output going to my address. So when you don't bind this locking script to a signature, pretty much people can swoop in and steal it.
So you can tell what the script is at this point? Because I thought last week you could not.
That's for SegWit transactions.
Okay.
And there's some nuances here. So for legacy transactions, the script pub key was the actual script. You took the script and you'd serialize it in bytes.
Everyone can see what it is.
Yeah, everyone could see what it
In
is.
SegWit, you have to know in advance, otherwise you can't use it.
Right, because in SegWit, it's pretty much a hash of the script that you put in the script pub key instead of the actual script. But another thing to keep in mind is that when Bitcoin was first released, the script pub key could only be one thing because everyone's policy only allowed a certain type of script pub key to go through, which are these script pub keys that like check for signatures. So if you try to put any arbitrary one, every node would reject it. The mempool just would not take it. So even though theoretically you could do a lot of interesting scripts, people didn't because everyone's mempool would reject transactions or scripts that didn't ask for a signature. Yeah, and I used that code for that, and I could have added some code for that, but I didn't, and I could look at some after if you have time. So what is the algorithm to convert a script pub key into an address? Has anyone ever heard of like any of these algorithms used? Maybe?
Base 58 plays into it, doesn't it?
Perfect, yeah. Base 58 is one of the algorithms that were used for, Yes, Bec32, and then there's like one other algorithm, which is Bec32M, right? Yeah, so Bec32M is used for taproot transactions. And I'll go over the legacy address generation. I'll also go over SegWit and taproot, so Bec32 and Bec32M, although those are more complex for one part, which is like this thing called the checksum calculation. So I actually don't go over that for the SegWit stuff. But yeah. So we can see how base 58 plays into the generation of legacy addresses. So base 58 has this very particular algorithm, right? And this is it. So you take a selected group of bytes, and then you convert these bytes to little endian. So I don't know if you guys like ever seen binary before, but it's like 1 0 1 0 blah blah, and it represents a certain number. Little endian is pretty much like when you reverse the order of that, and the number interpreted is the same. Or, it depends on the architecture of computer you have, or how you program things.
How you want to read it, basically. Sometimes it's useful to be able to read, the end first, and other times it's useful to be able to read
Yeah.
first.
So you could, interpret the same number in different ways depending on how you declare your byte, format. So yeah, base 58. You take a selected group of bytes, convert the bytes to little endian, which just like kind of think of it as like reversing for now. If you see a sequence of bits like 0 and 1, and then you interpret the bytes as a number. And then you do this process and you repeat it until like this quotient is 0. You divide the number by 58, and then you take the remainder and then you map it to a position within, is my mouse? Yeah. You map it to a position within this output text. And if you look in this output text, there are 58 characters, hence, base 58. And then finally, after you've done all that, you reverse the string.
Now, what do you mean by repeat until number is 0? Interpret bytes as a number. So like, you repeat until the interpretation of the bytes is the number 0?
Yeah, so like if you have some bytes and you interpret those bytes as a number, you take that number, you divide it by 58,
Okay.
and then the quotient you kind of use as the new number. And then the remainder, you map it onto a position in this string, and you add it to like our output string. And that's gonna be like the output of the base 58 algorithm. And then you reverse it at the end. And I'll give like a tiny example of this in the next slide. Hopefully, it sticks a little bit. So an example, this isn't bytes, this is really bits, that's a typo. But imagine, we have 0, 1, 1. This is the number 7. If you guys know binary, this position we'll add 1 to it, this one will add 2 to it, and this one will add 4. So 4 plus 2 is 6, plus 1, 7. And I just kind of put a 0 here. Oh, I think I might have forgot to put a part here. Interpret, did I? I don't know. Okay, I have it here. All right, well, I'll keep going. So we have these bits, 0, 1, 1. 1, and then we put it in little endian. So, like I said, you kind of reverse it. Then you take 7, you divide it by 58. What's that going to be? It's going to be 0. Remainder, 7. So very easy. You get position 7 of the text array below, and it uses 0-based indexing. So, like, the 1 is at 0, the 2 is at 1, and so on. So it's actually 8 that you're going to get. And then you add the leading 0 in the first step. So if there's any leading zeros, you add that as like a base 58 thing. So 0 always maps to 1. So you put a whole bunch of 1s at the end, depending on how many zeros you had in those bytes before. Then you reverse the string. So the output string was 8-1, and you reverse it to 1-8. And then I put a link here. But again, I have my webcam blocking people to live stream. Also, I just realized I don't have a chat open. I hope no one's asking questions or anything. Yeah. Let me see if I could get this open somehow really quick, even through my phone, I guess.
I can monitor the chat.
Okay, awesome.
So there's a part of me that like wants this to make a kind of sense that I don't think it's supposed to make. It's an algorithm. It's just like do this, do this, do this, do this.
Yeah.
And that's what you do. It's not like you do this because there's some like maybe there are reasons.
Oh, there are reasons to do this. Well, namely, let me go back one.
I think it should be mentioned that the reason base 58 was chosen is to eliminate arbitrary characters.
Yeah, it's to eliminate like confusion with some characters. So if you look, which number does like this string start with?
Is prem cipher funk radio?
No.
It just says cipher funk radio says Perry, Wing, Hole, Pirate here, all clear.
Okay. Well, hey, I'm waiting. I'll wait for him to come in. But yeah, I was saying if you look at like which number this starts from, it starts with 1, right? Why? Because 0 and
Capital O
yeah,
would be.
and it gets confusing. Yeah, so it does limit the character set. Like you said.
There's
It's,
no O in there.
Huh?
On purpose?
Yeah, because those things would get confusing putting them
There's
together.
No capital I and no lowercase L.
Yeah.
Okay.
So this is a limited character set. It's not all like 0, 1, blah blah. It's not all A, B, C, D. It's you have to eliminate some of these like characters to not confuse anyone. Oh, did I go back one? So there's a lowercase o, but you can never confuse it with the capital O or a 0.
Is there a lowercase L?
Huh? Yeah. So these are 58 characters in a sequence.
So the output ended up being like 1-8. Is that like a code for a hash or like a code for a script, or is that the actual?
This is just to demonstrate the algorithm. So I just took a
Okay.
7 and I said
Okay.
let's encode this.
But would that end up being like an if statement, like if this, do that, whatever?
There's no. What do you mean by that?
So like this base 58 algorithm is supposed to be like encoding, I guess, the script or whatever, right?
Yeah, it'll be used in the address generation algorithm. This isn't just
It's not
what
the
you do.
whole script. That's just
Yeah.
part of it. Okay.
Yeah, this isn't the full thing. This is just like a part of the address generation algorithm. And like you could typically do things like this like online. I don't know if I could show you, but there's like websites you could use. Let's see if I can get like a Safari window. That's not this one. So like you could look up base 58.
Sorry.
Base 58 encoder. This is a string encoder, and that's not what we want. We want a number encoder. Hopefully this gives us numbers. Let's do hex. So like we did 07. Is this? But had 00. 18. So yeah, if we go back here, you get pretty much the same things going on. And if you want to test like other numbers, you could go and put in whatever you want. So if you have a number that you want to put in, is 9. And yeah, the process is the same. So yeah, just encoding. I haven't gotten to the address generation yet. Yeah, how's it going? Let me go back to the slides. What slide is this? Oh wait, sorry, I have it here. Okay, so this is the algorithm for making a legacy address. The legacy addresses, we call them like pay to public key hash. That's like, the default address that were used in the early days of Bitcoin. So if you've ever seen these acronyms, pay to public key hash, it represents the output type for something. And here's the algorithm for making a legacy address. So first thing you do is you specify the version of the address as like this first byte. So in the first versions of Bitcoin, this first byte was 0, version 0. And then you take the hash 160, which is an algorithm defined in the Bitcoin code base, of the public key, and then you add it to the version byte. So first you get the version byte, it's 0. You take the hash of the public key, and you add that onto this version byte. You run the current bytes through SHA-256 twice. And then you add the first 4 bytes to the end of the version byte and the hash of the public key. And we call this like the checksum part. This is the part people had problems with. So this checksum part is protecting you from putting in an incorrect address. So if you actually mess up some parts of your address, like when you're sending money to somebody, there's always a checksum part at the end, which like has to be coherent with the rest of your address. So if you miss a couple characters and you try and send money to this address, your wallet will stop you. You'll say this is an invalid address because we know, because the checksum is wrong. Because if we hash 256, the rest of the address, it will not give the 4 bytes at the end as the first 4 bytes of the output. So it's kind of cool.
So what was the problem that people had with it?
Because it doesn't actually catch. I mean, it catches a good amount of stuff, but there are better algorithms for this. Yeah, that's pretty much.
So there are addresses that are invalid that it will not catch.
Yeah.
Okay.
Yeah. It's like also what's the definition of invalid here, right? But yeah, but yeah, you can like generate like a correct 4 bytes at the end, and maybe some of your characters are like flipped or they're not what you originally gave somebody. It's not like something that happens often, but they're like, we could do way better than just take the first 4 bytes of the double hash output, and that's what they ended up doing with the SegWit address encodings. Okay, yeah, so you do all this stuff, and then after you have the version byte, the hash of the public key, and then this checksum, then you can base 58 encode all the bytes. So remember in the slide before, I said at the end you reverse the resulting string. So actually what happens when you, sorry, I'm getting low. Did I move? No, okay. What happens when you reverse like this string, if the version byte is 0, and that's like a leading 0, then you could actually like always determine that something's a legacy address if you see a 1 in a certain place, right? And they kind of follow this for this next address type that I'll show you. But like that's a feature that like they want, that you could identify addresses by looking at like the first character. It's very convenient. Yeah.
So is there a reason why there's legacy versus the current thing? Were there problems or were there features that were removed, like in other parts of Bitcoin? Like for example, right, was there a point when things weren't always one-to-one? Because you're hashing almost like you're, like you take like fingerprints, right?
Mm-hmm.
It's rare, but people could have like, the same fingerprints, right?
Yeah.
The same, even like identical twins would have, whatever it is. There's always like 1 in a billion chance of something happening.
Yeah, it doesn't happen super often, and that wasn't the biggest motivation when switching address types. Well, the first time they switched address types, which I'll go on in the next slide, was so that they could handle these pay to script hash addresses. And
could that be a feature, not a bug, right? Like maybe you want to.
Oh no, you almost never want like a collision. That's yeah.
Maybe send something to a range of addresses, so more analog as opposed to like descriptive.
Mm-hmm.
Like last week's lecture or 2 weeks ago's lecture about like the covenants, right?
Yeah.
It could be like anyone in that range could claim that Bitcoin.
Yeah, although with scripts they work a little bit different because with the address you can't derive what script what was used. So I'll go into like the more types so you can get a better idea of, all this stuff. So pay to script hash algorithm. Has anyone heard of pay to script hash, the P to SH? Yeah. Can anyone give me a description of what it might be?
Also, like in the previous example, it was hashing your public key.
Mm-hmm.
This time it's hashing a script.
Yes. So yes, this time it is hashing a script. That is correct. Why was this address algorithm made? Again, going back to legacy addresses, the legacy addresses only work for like pay to public key hash, right? It's because Bitcoin would not allow you to have arbitrary scripts. Again, all these nodes were like hard programmed to only accept scripts that were in a particular format, which is like this pay to public key hash. So I think it was Gavin Andreessen who he could have proposed it. I feel bad if he didn't. Maybe it was like a lot of different people. I don't know. But I think he ended up making the proposal, if I remember correctly. And what he ended up coming up with, and we can look at the BIP after just to see who the author on this is. But he said, like, let's not use the same address type since we're almost giving this upgrade to Bitcoin. We're going to allow arbitrary scripts in. So why not have the new type of transactions that can have arbitrary scripts use a different address format? And the whole concept of like how this would work is that you could hash the script where you used to hash the public key, like Prem said, you just swap out, or blue banana, whichever you want to use. Pseudonym,
So this is a soft fork, right?
Huh?
Because if you said the policy before was to only accept pay to public key hash, now
Yeah.
they're changing that policy, so this is a soft fork, right?
Yeah, soft fork.
Because
Yeah, I guess, yeah, I would call it a
didn't
soft fork.
upgrade to this new policy would not accept transactions that were created using this algorithm, right?
Yeah. So,
And it was Gavin Andreessen.
okay, cool. Yeah, I would call it a soft fork. Things back then were like less contentious. People used to say Satoshi would even hard fork sometimes, whenever like it was needed. And there was needed a couple different times because there were some fatal bugs. If you came to my script, UBS, or Understanding Bitcoin source session, you know that there was some like very, very fatal bugs, like op return, for example, allowing people to spend anyone's transaction that included it. But you could force it to be included. I'm going a little tangent, but one of the things that were like forked out were op return. The way it used to work is that you used to have a script, and I would unlock your script with data or another script, and I'd put it in something called the script sig. And if my script sig I had op return, it would quit from the execution of the rest of the script. It would look at like my answer or my unlock script. They'd see the op return. It would skip the locking script, and it would allow the transaction to be spent. So whatever the previous person put in there would be skipped, and that was obviously very bad. So they actually changed op return to fail if you see it anywhere in the script, because it was like it was a kind of a stupid bug, but luckily it didn't break Bitcoin. So back to P2SH, pay to script hash. Yeah, when they were upgrading, when they were soft forking, allowing, I was like hesitant to call it soft fork because there's also things that are related to the wallet. Some people, they like to make a distinction, or a very important distinction, between the wallet in Bitcoin Core and like the node, so the thing that will maintain your blockchain and they maintain this mempool, and then where your keys are actually stored. I like to say it's like part of your node too, but some people make this distinction. But it's also a wallet change, right? Like there are some wallet changes, but yes, there for sure is a change to like your mempool policy and what is valid as a transaction. So it would be a soft fork. Anyway, pay to script hash. So in this one, you specify the version of the address as the first byte, and you would think that it would go, this is 0. Maybe you want to go to 1, right? And it's like, well, how about we do 5? And the interesting thing about 5 is they wanted it to encode to 3, because again, whatever you had for the version byte, it would go through the space 58 algorithm, and then at the end, this result would be reversed. So your version byte, like when you, first you do some little Indian stuff, reverse it, and you reverse it back, and then you'd end up with the version byte there. So again, these are things that they do to easily identify addresses. But maybe I'll go through the algorithm and I'll stop going on tangents. So to make a pay to script hash address, you take the hash 160 of the script that you wanted to use. You run the bytes through SHA-256 twice, so same thing as the first type of address I went through. And then you add the 4 bytes to the end as the checksum. And then you run this string through base 58 to encode the bytes. And then the first character should be this version byte 5, which will always encode to 3. So any address you see starting with a 3 should be a pay to script hash address. And a different version byte was used for testnet, and I forget what the version byte for that was used. So this is pay to script hash. There's a lot of motivations that went like behind this, and again, we could look through all these like bips as like a short thing at the end, because I'm almost done with these algorithms. But now we can go on to Beck 32.
Before we go on, what's the script hash?
It's the hash of the script. So like, which is, I guess not super descriptive.
Okay, so what is the script? Where's the script coming from? Because I get the pay to public key.
Someone writes it, right? Like, so someone creates the script, like a developer, they write the script.
Yeah, so like if I want to send Bitcoin to you, in the early days, my wallet you would give me an address that I could spend to, right? So your address would essentially be like a hash of your public key. That's kind of what I went through like before. But basically, you give me an output that I should spend to. But as a spender, I could spend anywhere I want, right? And let's say you didn't give me an address and I just wanted to do something fun. I said, this output, I don't want anyone to have a specific public key to spend this in a signature. I want to allow anyone who can unlock this locking script I put on to be able to take the funds and spend it however they want. So what I'd do is I'd make a transaction with a script pub key that contains, like some script, like, hey, give me the answer of 1 + 1. And then I would generate an address for that script from my own wallet to spend to. So I'd hash that, and then I'd put it through this algorithm that I just described, where you put the version byte, the hash of the script, and then this checksum at the end. Base 58 encode that whole thing, and then that would be your address, and then you spend to that.
Can you give an example other than 1 + 1? Like, so what is an example of a way that people actually used that?
People didn't really use these like scripts all that much. I mean, one of the
like, what's the point of doing it?
one of
You
the
can
famous
make a riddle, and whoever solves the riddle gets
Anyone makes the riddle is what I want to know.
Yeah. So I could show you. This is actually in my understanding Bitcoin source on script, but it is Peter Todd. I think I'd find it with hash puzzle.
I mean, the guy on the watching on Twitch right now, he's Periwinkle Pirate, so I assume it's maybe a pirate treasure map you encoded.
Periwinkle. Okay, hello Periwinkle. Where can I find this? Shawan Pinata? Is this? I just want to see the Bitcoin talk. Yeah, maybe this is it. I have it bookmarked in my other thing. Here, this is just for the first page. All right, Peter Todd. He has these scripts up, and a lot of these you could still answer today. So basically, as these hash algorithms started to be enumerated, and you could start finding collisions, he locked some Bitcoin early on that said anyone who could find collisions with all these different types of hash algorithms can provide the 2 different pre-images, and in his script, he'll hash both of them and compare them. And if the hash output for them is the same, you can claim the money. So like, people did fun things like this.
Do you know how many of them still exist?
Yeah, I mean, we could see which one. So, this is a pay to script hash address. We can go and we could look at this one, for example. I mean, this one's probably still up. This is SHA-56. But SHA-1, let's look at this one. Blockstream.
So that was a reward to like crack certain hashing algorithms, I guess?
Yeah, exactly. It's like a bounty, right? But again, going back to my example before, if you were to broadcast a transaction like this that's not bound as signature, and I'm a miner, I could steal it from you. and spend it to myself. Because all I need is the unlock script. I don't
And
need a.
that's still the case today, right? So like, if someone found the solution to those hash
Correct.
scripts,
Even after
the
SegWit,
miners
yeah.
can still steal it, right?
Right. Even after SegWit, because like when in SegWit again, I can spend to like a hash and no one knows the script unless I spend from that SegWit output. But as soon as I,
Screen is frozen.
oh man.
And so that's
Uh,
MEV, right? Like, isn't that that's
How about
is
now?
that an example
Did
of
it-
MEV?
Maybe it's
What's
just
that stand
not
for?
my phone.
Yeah, it
Minor
was
abstract
every time I try to
value.
watch, like I always have
Ah,
trouble with it.
really?
Yeah.
That sucks.
I figured it was just.
I think we're gonna need to like 2 devices in the future. One device for your presentation, one device for the live stream.
I think it's up. Mine is showing on. I mean, it could still have caused. Okay, all clear. Or maybe just resume. Did it resume on yours, Prob? Or no?
Maybe I'll just resume. Maybe it's just a bug in my phone.
Yeah, that's what I was thinking.
Because I'm on AT&T, it's not good signal here.
Okay. All right. Thank you, Cypherpunk Radio. Okay, cool. What was I doing? Oh, we're gonna check the puzzle. Yeah, this one I'm pretty sure is claimed. So people sometimes do funny things and they spend extra Bitcoin to these type of addresses. But yeah, as you can see, this has no available outputs. All of them have been spent. So people have spent 2.49 Bitcoin. Can you imagine if this is still available today?
And you were saying that like so
It's like
people,
80 grand.
People put more money into
90.
90, yeah.
that.
Yeah,
address?
yeah. Sometimes when people see like a bounty, they'll put some money into it, and they'll see like, who can unlock this, give them more incentive. So, but sometimes people just do things like I've seen the cases where someone's put an arbitrary script and put on Twitter, hey, go get this, and someone already unlocks it, and someone puts more money in afterwards to have someone unlock it in the future. Even though, if I went to their address page, I could see the unlock scripts of all of the things before it. So it's not really valid anymore, but yeah, this accrued 2.5 Bitcoin. So yeah, too bad it's not available, right? But there's certain things that haven't been cracked. For example, we do not have any SHA-256 collisions. So this one is still here. And unfortunately, people haven't put more Bitcoin in
They
here.
knew better.
But even if they have, I don't think anyone will be able to redeem it.
But what's the thing to solve?
Find two pieces of data that hash the same thing. So it's what we call a collision.
Oh,
So if you could find a collision in SHA-256, then you could spend this transaction.
to see what was run through the shop 256.
Yeah, because it's very, very hard to find a collision. There hasn't been a collision found for SHA-256.
And like usually, if you can find one,
Yeah, you start looking for another. Yeah, you start looking for another hash algorithm, pretty much, because that's not as desirable property most of the time.
Alternative, like SHA-3 or SHA-1,
no,
something.
SHA was an excellent.
Yeah, there's like SHA-512, but like each of them, there's like a whole bunch of hash algorithms.
SHA-1 had collisions.
Yeah, SHA-1 has collisions. It's not good to use. Shouldn't.
Yeah, and that's why they were able to solve those.
Yeah, but there's like advantages to some. Like sometimes I don't care as much if there's collisions, if it's fast. MD5 is something used a lot to like verify files and programs you download from the internet. Yeah, different use cases.
Eventually, these should be found, right? Computer
I mean, given enough time, right? Like towards infinity, Well, yes, humans will find out collisions. A million years, 2 million years. If
So you can just update the algorithm here, I guess, right?
yeah, you'd have to keep like making Bitcoin better. Bitcoin cannot ossify.
But there's a lot of, but the implications are that like if SHA-256 was broken, then all of the addresses that were created using SHA-256 would now be potentially compromised, and so like.
But that's still like okay. If I found a witness program or something, I could like know what the program is. If I could brute force some scripts. But even that is would still be pretty hard, even with like only one collision found. But of course, it would signal for us to move. But if with our regular system where we have UTXOs protected with our public keys and having requirements for a signature, that will not be affected by breaking SHA-256. Like signatures should still be Okay, but there are some security assumptions we make with hashing things.
So Cypher, Periwinkle Pirate says, Namecheap's using SHA-1 for DNS security. Should I be worried?
I mean, I don't know how they're using it. I honestly don't know the DNSSEC protocol. So it all depends how you use it, you know?
So say Periwinkle Pirate today put in his pirate map or his will that like some Bitcoin for someone who finds his treasure, right?
Mm-hmm.
And Space Pirate 200 years from now finds the treasure map. But could it be the case, since there's so many forks and changes in technology, that map will be useless? Or could it be a case there's like Bitcoin addresses in the future that just won't be accessible because it's just a legacy code that they're using?
Yeah, but
Even today, are there Bitcoin addresses from originally Satoshi's time that we can't access?
yeah, but that's mostly because like I could also just make a random public key, right, and like ditch the private key, and no one can spend from that either. Like there's multiple ways to make unspendable addresses. Hashing isn't like a huge way to do that. The easiest way would just be to create a key pair and ditch the private key, and no one can spend that because it's very hard to find a private key just from a public key. Near impossible. Otherwise, Bitcoin would be broken.
I think what he's asking though is like about
Yeah,
backwards.
because,
It's about backwards compatibility.
Yeah,
so
yeah.
Today, if I understand correctly, like most of the more recent forks have been backwards compatible, and so like as long as we keep doing that in the future, then that should still be valid.
So we're still relying on developers, so the pirates should still be bearing gold until.
Yeah, I mean that's what we're doing when we spend Bitcoin, right? It's like we're burying gold. You know where it is. Like your private key of your wallet can sign off on it. That's almost like in the location, or you'd be able to spend it. But like digging it somewhere, and as long as you're alive, you could spend it. But if you die, then the map that you need to identify the treasure, or in this case, be able to spend your UTXO, is going to be gone. So you better not die, or if you do, have someone else have your keys.
So many the metaphors that people use in Bitcoin lore is it's a time machine, right? Or it's energy through time and space, right?
Yeah.
But we're reliant on developers keeping that metaphor going for perhaps ages, which maybe they won't do.
Well, that was always the.
I don't know that it's really like developers per se, but it's just you would think that there's someone willing to mine your transaction on a chain in the future, right? In the future could have 100 different, Bitcoin forks, and maybe the popular one, hard forked away some stuff that, now you can't do. But what we think is, that there will still be a Bitcoin, that will accept your transaction if it's valid today.
Yeah, because in a way, like if you accept an upgrade that invalidates previous address types, then like now miners are denying themselves the possibility to to process those transactions in the future, and that could be like a lot of Bitcoin.
And if you have an old transaction for miners, it's even better because they have to process more data and charge you more money.
Yeah.
Can you imagine all these people who've lost Bitcoin in boating accidents? That could be the new salvage operations. Like people are finding billions of dollars of Spanish galleons. To find Prem's buddies sunken.
Right.
Bitcoin
Or the joke, lost in a boating accident. Yeah. But yeah, if you lose it, it's gone. But yeah, ECDSA, the signature algorithm, isn't severely put into a position where it can be cracked just because SHA-256 is, and it would put money at stake, right? Because if I was able to find arbitrary pre-images to reach an output, then I could start identifying nonces very easily when I do my block hash, right? But yeah, I guess that's the implication of breaking SHA-256. But yeah, these things can be broken, or pretty much we can catch up in our compute to be able to start cracking these hashing algorithms. So yeah, some people want Bitcoin to ossify, and it can't completely if you want it to be secure, depending on how long you think Bitcoin should be traveling into the future.
Wait, what's that mean, ossify?
Yeah, it means don't touch it. Like this is it. We're solidifying the code base.
Like
And,
set it in stone.
Okay.
yeah, some people say, oh, like some people will allow patches, which obviously makes sense. It's like you need patches. It's a security bug, but it's like what does patches? What do they entail? Does it entail an upgrade of like a hashing algorithm? And different people say different things. A lot of people don't understand that like things like SHA-256 can be broken given enough time, right? Because we will get more compute as we approach infinity. So like, I don't know what people mean when they say ossify, because you can't. Things like this can't necessarily always be ossified and be secure or functional. But here, I'll wrap up with these SegWit addresses. So back32. There we go. So back32 kind of differs from pay to public key hash and pay to script hash algorithms. So how they work is you take a human readable prefix. So something like BC for Bitcoin, that's why it's chosen. It's like kind of funny. If you look at the bib, they're like, oh, why didn't you choose BTC? And they're like, BC was shorter. It's like, kind of stupid. And then after you have the human readable prefix, you add a 1, and then you add the bytes of data you want to be encoded. And okay. Yeah, so this is just the back32 algorithm. This isn't how you make addresses yet. Just like for the legacy addresses, base 58 was used in the process. It wasn't the only thing that happened. In the same way, back32 is used in the address generation process, but there's more to this to generating an address. So yeah, back32, you take the BC prefix, you add a 1 to it, and then you have some data, right? And there's some prerequisites to this data for reasons, which I think you'll see as I go to the next one. But it has to be at least 6 characters, and it can include the characters 1, B, I, and O. Again, it's easier that way. But then you compute a 6-character checksum using a BCH code algorithm. See, I know it looks like Bitcoin Cash, but BCH is an acronym, and it actually stands for this longer algorithm name. It's an algorithm that was defined outside the scope of Bitcoin. If you're interested in the actual name, I could list it here. I don't know if any of you guys actually care, but that's sitting on my own computer. Oh, I hate this thing. It keeps blacking out. BCH code. This is it. If you just look at BCH code, you can see this checksum algorithm. I didn't go over it in my slides because it's a little bit more involved than I wanted to go into. But you could look at it if you're interested, these BCH codes. Bose, Chaudhry. I don't know. How do you say this? You want to give a crack at it?
No, it's Chaudhry.
No, this one.
Hopkingham?
Yeah, maybe. I don't know.
Smart people always have hard names.
Yeah, that's he's a genius.
The names sound like South Asian. Interesting because, like in India, like until really recently, there weren't really addresses. So I'm wondering if like they over-optimized for their childhood. Like for example, right? Like if I write a letter to my, relatives, I have to describe where it's going. It says, behind the yellow building, behind this big tree, literally. Villages. I'm sure maybe it's different now, but thing about it is when you grow up in that universe, in that world, your worldview is people like develop a sense of direction really good. So there's a whole like documentaries on like the lunch times in Mumbai. Basically, there's a whole like ecosystem of like runners who will take like lunches of business people from their wives at home or etc. Every day, millions of people get their lunches with no real Uber Eats for everyone. The whole city.
Yeah.
Without any directions, they know exactly which cubicle someone's in, how to get there, and it's always on time, always hot. It's got to be delivered in 30 minutes, and it's amazing with no addresses, no nothing.
So
I'm wondering,
their perspectives changed because they didn't have static addresses and they had like a more descriptive way of going about things. Yeah, maybe that inspired, invention of a checksum.
It'd be interesting if they put an Easter egg in there too.
Yeah,
Type Easter egg.
Yeah, I could go more into these BCH people, in another session. But again, it's a little bit complex. That's why I didn't want to go through it here. But yeah, this BCH code algorithm does what that double SHA-256 did before. So you know how it like gave a checksum at the end? So if you messed up one character of the rest of your address, that checksum would catch it. This BCH algorithm is a lot better than that double SHA-256 and taking the first 4 bytes. Yeah, that's why they chose it. They're like, you know, let's ditch the old way and let's just go for these Bec32 algorithms for SegWit. Okay, now, you know, internalize this Bec32 algorithm. You know, use the BC and remember the 1, and, you know, you put some data and then you have the 6-character checksum, right? Because we're going to use this in the next step. So Bec32 is Bitcoin, like it was created in the Bitcoin world. BCH code for the checksum was not, just to clarify. All right, so now we're going to be using Bec32. I know, one second, I have my webcam covering, but I think, let me just move it up here. Because I think this table's important. So yeah, SegWit v0, pay to witness public key hash. Sorry. No. Sorry, I was moving my webcam around the screen while I read. SegWit v0, pay to witness public key hash, and oh, I messed up here. This is supposed to say pay to witness script hash, but yeah, so this is a typo. And they're defined in BIP 173. So these address algorithms, or it's just 1, the Bec32 algorithm. Where this address generation algorithm that incorporates Bec32. So the way it works is you get the witness version. So in SegWit, it introduced like this new versioning system, which is like the witness version. And you get the witness version, so SegWit was v0, that's like the thing that caused the fork. And then you append it with the script hash or the public key hash, because SegWit defines both of them in their own way. So it's a twist on the regular pay to public key hash and pay to script hash. So witness version, the hash of the script or public key, and then you split the bytes from like the sequence of bytes into bits. So like the 1s, and 0s. And you group the bits into groups of 5. I know this is like a little bit more granular. And then you add zeros to the last group if it's not equal to 5 bits. So like, if it's uneven. And then 5 bits can represent 32 different numbers. I wanted to say this. So if you have like 5 zeros and 1s in big endian, it can represent 32 different values, the values from 0 to 31. And then you map each sequence of bits to a character in the table to the right, depending on its value. And this is kind of like weird in that, like, this is 0, right? This is 1, this is 2, but there's no sequencing here. Like, it's not like the other one where it tried to keep like A, B, C, or like 1, 2, 3. It's like Q, P, Z, R, Y, 9, right? X, 8. It is like, what's happening here? And if you look at the BIP, they actually had a justification for this. When they said the ordering is chosen to minimize the number of pairs of similar characters that differ in more than 1 bit. So, yeah, like when you have these groupings of like 5 bits, he didn't want like similar. Do any of you guys know what the Hamming distance is, or like? When you have like different groups of 5 bits, let's say they're both 0, and like you add a 1 to in the second one, then you say that there's 1 bit that's different, right? That's like kind of like this Hamming distance concept where you can have a number of bits that are different. And the way that these were enumerated, these letters, are such that two groups of 5 bits that look similar or have like a smaller like Hamming distance will be very different in the way that these letters look. Did that, yeah?
So you don't accidentally have one that's like too close to each other?
Right, yeah, you don't want similar looking letters. You want to get them as different as possible. And maybe this seems contrived or not necessary, right? But yeah, I don't know, this is kind of a cool thing, right? And then finally, I'm going to end off on Bec32M. And I'm lucky that I truncated this presentation to not have descriptors and miniscripts. Bec32M. This is what's used in Taproot. So Bec32M algorithm is almost the same. It's practically the same as Bec32. Only difference is that there's in the BCH code algorithm that generates the checksum, you replace this constant that uses 1 with this hex value. And it seems kind of arbitrary and weird and like random, but this actually helps with error detection. And I haven't looked into how it works. I think Peter Woolley might have done this BIP, and the big brains understand how this works, and I haven't spent time looking at it. But yeah, if you swap out some constant 1 that you used to XOR within the Spec32 algorithm with this value, then it would make error correcting a lot better. Hey, how's it going?
I think you called my name, but you said error.
I might have, like maybe in my subconscious. Yeah, I could have said Eric. Yeah.
Can you go back to that, the thing you want to hide, yeah, right there, yeah.
Mm-hmm.
So, that's more than 5 bits right there, that's 8 bits. In your
This table?
the table, yeah.
Uh,
0 to 7.
Well, so with 5 bits, you can make 32 different values. Value 0 to,
2 to the 5th,
which is 31, right? So like this first row is 0 through 7. This second row has the offset of 8. This last one is 20. The biggest number is 24 plus 7.
31, yeah.
Right. Does that make sense?
I'll have to look at it closer, but yes.
There
Yeah,
are
I've never heard
32 numbers there, is what it says. Basically, 32 characters.
Awesome.
Oh yeah, there's 5 bits, and with 5 bits you can represent.
So 8 times 4, okay.
Yeah, like it's I know it's written, it's like made in a weird way, but like if you like don't even look at these sides, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, blah blah.
Yeah. So that'd be a great for your treasure map, like have a bingo card and hide the code in your bingo winning bingo card.
Yeah, you could do something with Bec32, like this.
Just like put the star stamp.
Yeah, it could be fun. If someone wants to do the BCH code algorithm at the end as part of the Spec32.
And you're famous, man. People you on Twitch saying you're stuck at the back door.
Uh-huh.
So you're
Oh,
normalized on Twitch.
No one's stuck at the back door, right?
No,
Oh,
I
okay.
just pulled the person who was stuck.
Oh, okay, cool.
Why am I famous?
No, because other people were telling us they were there.
Yeah.
Okay.
All right. Well, almost done. Bec32M, we replaced this 1 in this XOR as part of BCH code with this hex value. Again, seems arbitrary, but the big brains say that this is better for error correcting. And then now we can get to the SegWit v1 address algorithm. And it's pretty much exactly the same as the SegWit v0 algorithm. So, not much changed. Except the witness version used to prefix the hash is 1 instead of 0. And now we use Bec32M. So remember, we as part of like the data part, or the thing that we Bec32 encode is the witness version, and then either that witness public key or the witness script hash. And yeah, that goes into the Bec32 algorithm, and then we get the address. This changed it so that witness version is going to be 1, the script hash is going to go after that, and then you're going to run that through the Bec32M algorithm to get the checksum. Yeah, that's pretty much it.
What is the M?
The M is this one tiny change that makes error correcting better.
1.
Oh, no, this is the
okay.
Bec32M. Remember the address generation algorithm was different from like the Bec32 algorithm. Yeah.
Fix a little bug.
Yeah, it makes error correcting better. The Bec32 isn't bad. It's just that it could be better, and that's why they made Bec32M. And then, wait, is this copied or did I? Yeah, this might have been copied by accident. And then I had some things that was inspired by Prem. But I was gonna close that. It's like 2 more slides I actually have. Why does pay to public key hash script pub keys are preferred by like wallet devs? Why is that the default for most wallets? And it's because they're cheap. Legacy addresses had a very concrete script to it. And if you actually look at witness pay to witness public key hash addresses, they're actually cheaper to spend than the legacy ones because they use less data, and you actually don't need this like whole script. It's like implicit. So it was interesting how they designed SegWit. It's trusted and battle tested, so most people use keys. But I use Green, for example, for a wallet, and they use pay-to-script hash addresses. Why? Because they do like a decaying multi-sig type setup. They don't actually use the multi-sig opcode. It's they check for their public key. I think it is, and well, Green has a server with its own keys, and pretty much after a given amount of time, you could just spend it alone. But before that, you need Green's approval, and they do this so that you could have extra security features. Like I don't want, you could tell the Green server, I don't want my Bitcoin to be spent for transactions over like 0.2. And if there is a transaction like that sent to your server, send me an email for two-factor verification. So like some wallets do get a little bit more advanced, but with this key scheme, it kind of works.
You can't do the decaying part with the regular check multi-sig opcode, right?
Right. Yeah. You need.
That's your point.
Right. Yeah. You need some type of like.
Time lock.
Yeah. You need to check the time. You need an opcode to check the time with, and multisig does not allow you to do that naturally, which is why in Taproot they dropped the like check multisig altogether, and you can only do check sig add, which is kind of the like script paradigm that Green uses.
Couldn't you do like a bunch of if-else's with different check sig parameters?
Yeah, but then it'd be more expensive because your script would be bigger.
Okay.
So yeah, that's they decided multisig was not something they wanted to use. That's why check multisig was dropped from Taproot altogether, and they have the check sig add, which uses this more efficient method of just using the check sig operation, which gives you a 0 if the signature doesn't match, and it gives you a 1 if they do, and you could like start adding these things together. But yeah, all right. I think I said 7:15 is the end, so I'm gonna wrap up with this.
We had the Nelson's question.
Oh.
DMD, the question.
Oh, okay, yeah, and I'll go over that as soon as I'm almost done with these. So if the public key leads to an address, why is it my wallet shows multiple different addresses? And this is a question inspired by Prem, and I kind of answered it, but there's a scheme called hierarchical deterministic wallets that allows a wallet to create multiple different private keys from one master private key. Each child private key can have a child public key, of course, because all you have to do is like this private key is really this number that you multiply with this generator point to get this public key. And yeah, each child private key can have a child public key. An address can be made from them, and typically this is how a wallet has multiple different addresses, because it's generating multiple different keys. But there's a scheme for generating these keys. So actually take the master private key, take it into a different wallet, and have it generate all these child public keys for me again. And it uses these things called derivation paths, but there's standard ones that will get enumerated through when you switch a private key from one wallet to another. And then yeah.
Unlimited? Can you make unlimited like sub key sub address?
Virtually. There's limits to things. Yeah. There's limits to how many addresses your wallet would generate, but you'll never reach it.
Recently, I saw someone write that there was 100 for a particular wallet, that it would automatically do 100.
Okay.
Mm-hmm.
No, wait.
Well, for wallet searching, for wallets that search, because if you're generating the derivation paths, you don't have to enumerate all of them, right?
If you use like 100 addresses, your wallet's just going to generate another 100, right?
But if you first import your private key in front of the wallet, sometimes like as default, they'll like enumerate only up to a certain point.
Oh, for
Like maybe there's an option that says, hey, look through the next 100
like a legacy
generated.
wallet?
No, just like any wallet. Like if I have a master private key, and you're like, let's say you're my wallet, and I give it to you, how many addresses are going to generate for me?
But you gave me the XPriv?
Huh? Yeah.
No, like this
like
is-
you're my wallet.
And
Well,
I can
in this.
then I can generate them myself, right?
Yeah, but like, do you want to generate all of them and query? Like, I don't know how your wallet software works, but you're gonna have to query this. Like, maybe you have a private Explorer instance. It's gonna have to query every single address.
I mean, think about it like this, right? Like, it can generate an infinite number of addresses.
Near.
What?
I said,
Near
or like,
infinite number of
yeah,
addresses.
to you as a
But, like,
human.
So if you're trying to load your private keys to a new wallet, like you would not be using like the the 750th derivation address, like you'd start from the first one, right? Like, okay, it created an address for you, then it created a second, and it created a third. Like, how many?
So, but it's like this. You take like your private key and you append your index to it. You got a derivation path, right? It's like, you know,
Yeah.
whatever 86.
Well, so yeah, but Prem's not saying that like you can't get more addresses. He's just saying what's practical for a wallet to like look through when you import a new master private key.
That's probably
Like, have you
the
used
primary
100 different?
resources of your computer.
Right, but like by default, these softwares have to be like it has to be hard coded, right? It's not a random.
Default amount.
Right, yeah, and I think that's what Prem was saying. The default typically is
As
100.
soon as you approach the limit, the default limit, it's just gonna get some more. It's like,
But it wouldn't know to get some more, right? Like,
yeah, but.
right, maybe there's a button or something for like me to search these extra 100, but like there has to be some default. It's not gonna iterate till 1,000,000. It has to have some.
It's like,
yeah.
it's like you go on Instagram or whatever, and it's like how many stories are preloaded, and
Right.
all you do is doom scroll, and you don't even notice that it loaded more in the background.
Right, but your wallet does not doom scroll, or else it would waste computation looking 1,000,000 plus addresses, right?
Consider that if you're
But yes, it can.
if you're loading private keys to a new wallet, this wallet now has to look at the blockchain to find all of the transactions that you've
Or use an
created.
API. If it, like, you know, like I said, Explorer is you can run a private instance and that indexes things for you, and it's quicker that way.
I have a wallet.
Well, I mean, but ultimately, like, it can do a near infinite amount of addresses, but you don't want your wallet looking for a near infinite number of possibilities. Like, you.
It's so convenient to just make a new wallet if it gets bogged down because you like are a super spender or whatever.
Yeah, but I'm saying in the instance where you needed to reload a wallet to, you know, what do they call it, sweeping or something? It's not sweeping. What is it when you load a wallet?
Consolidated
Mhm.
import.
Yeah,
Yeah,
import.
Yeah,
Yeah.
when you import a wallet.
Yeah, so there's a certain amount of addresses that's generated, whether like, you know, you want to find the first 1,000,000 addresses as per these derivation paths, or you want to find first 100.
Yeah, it definitely gets bogged down.
It's an arbitrary choice, right? Like it's by the wallet developer. Anyway, I just wanted to mention that, and then I was going to go. So I got a question about how can I find the average.
Actually, I have a question about his question. Yeah, Nelson's a little bit off topic anyway, but it's a really good point because like we made a wallet also, not for Bitcoin, for a different blockchain, but like this is a different concept here than what I'm used to. So I know the concept is you're not supposed to reuse your addresses. That's why you want to have so many.
For privacy, yeah.
Yeah, but then when you're saying like sweeping or consolidating, how does that actually work? Like per se, like say I made multiple vending machine transactions, right? And each transaction, even the failed ones, has a different address, right? And then in my wallet, how do I know what my balance is? Because I have all these addresses running around in my wallet. And what if now I want to just import my private key to a different address? Does it have a block explorer built in? Like it seems like I have all these transactions running around the entire blockchain, and a block explorer is not going to traverse the whole thing, or do they?
Oh, you're saying.
Certainly can.
The wallets add up what's in all the different addresses.
So I
you
guess-
gotta keep a record.
Wait,
of,
but
like,
so that goes to the
10,000 addresses.
No, so that goes to the derivation paths, right? So like it has your private key, and then it's going to run an algorithm one time to generate the first private, you know, the first address. Then it's going to run the algorithm to generate the second address, and like it's in order. And so you know you might not necessarily use every single one that it generates, but it does generate them in a certain order. That's the only way for when you load, you know, when you load the wallet to a new, load the address, the private key to a new wallet. It's the only way for it to be able to find it, because again, there are a near infinite number of addresses that it can generate. So it has to do it in a systematic order. Otherwise, it would be computationally oppressive to try to find your, you know, all like you'd have to run all of them.
I don't know if you guys talked about the gap limit. Did you mention that? Heather, like when your wallet is looking for these addresses, there's a standard like gap limit that it's like, all right, if I can't find anything, like any additional addresses for like another 50 or additional like
Stops.
with balances, it'll just stop.
It's gonna
50
assume
is
you're
like one of
using
them.
them in order
Yeah.
sequentially.
So it'll keep and it'll skip like a couple, like right.
Yeah.
If you don't have any balances, like you
Well,
may
so
generate it to, like,
I'll start by
100
saying,
number
yeah,
that I said
yeah.
earlier.
Prem was saying the default was like 100. So like even if your gap is like 10 or something, you'll enumerate the first 100 anyway, and then like maybe that'll start kicking in. Where it's like, oh, we noticed
So
one.
literally,
Uh-huh.
I always wonder about this, literally, like when people say like they lost their wallet in a boating accident, right? I always thought it was just, well, how do you lose that? Because can't you just like write down your private key?
That's
That's what they're saying, they lost their private key.
Yeah.
They wrote it
Right.
down and then their house
But
caught
this-
on fire.
In this
Alright.
case, it's not though, because your wallet is actually storing information beyond the private key.
But it,
Yeah, but if you can't restore it, or you lost the device that the private keys were on, like say you put your code into a phone, and then now you've lost that phone and you lost what you wrote down, then that's it.
Okay, but say I have the private key like in a safe deposit box, right? But I lost everything else.
Then you're good.
And
It's
then
just
now-
being
now-
on the
What is this
computer.
else? What else do you think the wallet stores?
Say I had $20 and I had $20 or
So
20 Bitcoin
So you
today,
have the
right?
one private key,
Right.
and then there's a hierarchy, right? And it like there's a standard path, right, from that hierarchy, and it just says all the private keys are derived from the one private key, the xpriv. So you derive the rest of the private keys. I wrote a wallet like a couple weeks ago, from a class learning how to do this. You have the one key to rule them all, and you generate like the first 2,000 private keys from that, and if you want to import it to another wallet software or whatever, you just need the one private key, and it can do the exact same computation and get the exact same 2,000 private keys, and then it just scans the blockchain from like some point back in history, looking for any money sent to any of those 2,000 keys, and it just adds it all up, and it can do it on any new wallet. It'll always like get the same information because it's reading from the same blockchain.
No.
So it doesn't store anything except for maybe labels if you want custom labels, and that's private in your wallet. But
It's pretty interesting.
Now, one thing to note is that the derivation path, right? Like there are standard paths that we use, but if you do use some non-standard path,
Yeah.
you might lose your stuff.
And, yeah, this wouldn't be
You're
something.
on a
Yeah.
computer, you don't search
Your wallet would
for it,
never
it's
do this most of the
computational
time.
stuff. There's a great
Uh-huh.
website called walletrecovery.org, I think it is. If you Google wallet recovery, it's got all the popular wallets and their derivation paths. There are a few standards, but for example, like Samurai Wallet, one of the things they do is
Yeah.
they have these separate accounts for different for different time, like different states of the mix that you're in, right? So they don't want you to spend something that hasn't been mixed with something that has been mixed. So they separate this into different accounts. But those accounts have like custom derivation paths. So if you put your Samurai seed into like a standard wallet, only a subset of your balance will show up on that wallet. You're gonna have to put a custom derivation path in order to be able to unlock the rest of it.
and we don't want to get into.
Yeah, if you're doing all that, you need to.
Huh?
you need to-
Right. Yeah. Originally, I was going to include descriptors, and in descriptors you could specify. But yeah, there are standards for derivation paths, and I did bring it up when I first went to the derivation path stuff. You could go with custom derivation paths, but it's not recommended.
Do not.
Yeah, exactly. Pretty much that. Do not,
Do not.
because you lose compatibility with all these other wallets, right? That's why standards are
One
created.
thing that I'd love to add here is part of the neatness of the hierarchical deterministic wallets is you don't actually need the private key to get balance totals. You can actually start with like an XPub or a ZPub and derive all the public addresses without
To
having
get
the
your
private.
balance.
To just get a balance.
But
So
to spend,
you might
like,
go-
you need
right,
the
to spend obviously you need the private, but you'll see like a lock only wallet show up in
how's it going?
terminology, and that's exactly what that is.
Yeah. All right. I think I'm gonna close this out just because we're gonna start bit devs soon.
Can we do a 10-minute break?
Huh? Yeah. Let's do a break. Okay. I'll answer. Yeah. That one question.
Yeah, so Nelson is from,
Yeah.
he hosts a Palm Beach Bitcoin, and he also wants to do like a Jeopardy game show type of a community. But he's about to go to Bitcoin Beach. He's for the halving wants to rent Airbnb for all of us down there. But anyways, he has a question from.
Yeah, so the question was how can they find like the average time to mine a block within the last 500 blocks, right? Every block has a timestamp. Most miners are pretty faithful to the timestamp, although you could like fuzz it a little bit as an extra nonce, but people typically don't go too crazy with that. So if you wanted to do it programmatically, you could look at the blocks, the last 500 blocks, get the timestamp of each, and then get the average time between each of these blocks timestamps. So that might be a good approach for them to take. Yeah.
Was 500 an arbitrary
Yeah.
number? Okay.
All right, so I'm gonna stop the stream and we're gonna get ready for bit devs.
The restroom is just down the hall for anyone who needs.